Okay, so we're ready to get started on today's colloquium. Today's speaker is Dr. Sergei Tochitsky. He's received his PhD in laser physics from the Institute of Physics in Minsk in 1992. His phone's just ringing there right now. He's been at the UCLA Laser Plasma Group for many, many years, and he's the senior scientist in charge of the Neptune lab. I've actually been in that lab. You have to go into a bunker to actually fire the laser. So he's obviously an expert in high energy, long wavelength laser sources. And today he's going to talk about long wave infrared filamentation in air, and in particular lasers and high field phenomena. So Sergei, please. Thank you.
Okay, let's first sort out it's a very small lecture hall, so I don't know why. Mic is, do you hear me nicely? Okay, cool. Well, first of all, it's a pleasure. Second, it's a short flight, and I enjoyed it because it's a short flight. But at the same time, today we're going to talk about long wavelengths, infrared, and I even wanted slightly to change the title of my talk, but then I thought we just sort it out on a fly. So for life, I'm dealing with long wavelengths infrared pulses and long wavelengths infrared radiation. And the question is, why in the world we need to actually, what is the interest to do that? And from a prospect of a high field science or strong science, we're interested in long field, or excuse me, in a long wavelengths infrared, because electron, either free electron in a plasma or electron in a solid state, it always oscillates and following scaling of I lambda squared of Ponderomotive force. And what that means? It means if you make electron oscillate so fast that its mass becomes different from the rest, mass of the rest of electron, which is called relativistic laser interaction, that for 10 micron, it just happened to be somewhere around A naught equal to 1. A naught is a normalized vector potential, which again describes how this number 8 oscillations are coming when laser interacts with free electrons, and it is 10 to 16 watt per square centimeter. Of course, we're talking about here intensities. Second important thing, something that we have been exploring for at least on my time at UCLA for decades, is to actually apply that high field for acceleration of particles. And here comes a second important advantage of long wavelengths in comparison with short wavelengths, so-called critical density of plasma. So if you ask yourself a question, why can't you see through the wall? From optics standpoint, it comes from the fact that for visible light, refractive index of that particular wall is 0 or tends to 0. The same happens when we ionize gas and we have plasma. And when plasma frequency starts equal to laser frequency, it is a condition called critical plasma density, and that for light means light cannot propagate through. So that type of densities is just 10 to 19 cc. One can say, so what is the scale? In this room right now, the neutral density of gas is 3 times 10 to 19. So we're looking at a gas that actually, if we fully ionize it, can work as a beautiful wall, and I will show you some interesting application of this. And the third one that came recently to us is actually, if you ask yourself, if you want to propagate over long distance laser in atmosphere, you're looking at transmission windows of atmosphere, and it is very well known fact, famous transparency window from 8 to 14, and some from 3 to 5, for example. Again, mid-IR has superior parameters of transmission. However, on the top of it coming some additional advantage on having the smallest molecular and aerosol scattering and turbulence scales approximately like lambda. So longer lambda will make you more immune of turbulence. Based on that, I build my talk today on three important kind of punching points. So first, I would like to explain to you where we are with long wavelengths, terawatt power lasers. Second, I will give you just one example why we need that and what can be done when we actually build one of them. And I will finish, and my main part will be on nonlinear propagation in atmosphere and recent experimental data we got in propagation of long wavelengths radiation in atmosphere. Okay, let's start with lasers. Well, if you look at a spectrum of a CO2, it always consists of multiple lines. Lines correspond to different raw vibrational degrees of freedom. For example, CO2 laser at 10 and 9 micron will give you a family of lines. For one branch, it's shown up here. It is exactly what happens with CO2 that we're increasing right now generate in this room. It is basically spectroscopically is just a comb of individual lines. Each line has 3.5 gigahertz. And in order to amplify high power pulse, we would like to amplify pulse as short as possible. You perhaps heard last year Nobel Prize for CPA, and which was enabled by existence of very broadband media. Why it is important? Because the broader the bandwidth, 1 over delta nu, which will give you the shortest possible pulse, you can get very short pulses. And therefore, you don't need to push energy high enough to amplify very high power pulses, which is what we're interested in. Well, if you're looking at what could be the easiest thing, let's just pressurize it. So if we're going to 10 atmospheres, for example, as you see lines overlap, and eventually at much higher pressures, we just simply get a nice, beautiful bandwidth for amplification of a short pulse that is suitable for amplification of pulses as short as 1 picosecond, for example, for P branch. The problem is that we have an issue in getting inverted medium at very high pressures. Typically, historically, it is done using electrical discharges. They contract or they streamer. It means we cannot excite in a large volume homogeneous active medium. Well, we pursued an alternative approach. We said, okay, if we have high enough laser already, let's say 10 gigawatt per square centimeter, then it is another term that should be taken into account to consider total bandwidths, and that is a power broadening. It is something related to AC Stark effect. Of course, that broadening exists only during the laser pulse, but we need the bandwidth only during the laser pulse is present in the medium. So I don't need to have a bandwidth before and after the pulse. That doesn't matter. And as you see, it's quite efficient way at 10 gigawatt, we're getting bandwidths actually corresponding to 10 atmosphere pressure. So now we developed many years ago a strategy to build a high power 10 micron gas laser where when we stay low on energy and power, we must have high pressure. Once we ramped up an amplified pulse to say millijoules in picoseconds, it's like approaching hundreds of megawatt and gigawatt level, we ultimately don't need that high pressure, and you will see that it does work. Well, here is a schematic of a system that we have built at UCLA Neptune Lab. It's rather complicated. I don't even try to describe what you see here. Don't even try to memorize. For you just to understand what is important here, as any high power laser system in the world is built, regardless of active medium, you have so-called master oscillator power amplifier system. So you have to start with generation of a seed pulse, and then you slowly but surely ramping up the energy and power of that seed pulse to a high level. The only message to take from this view graph, we are not using chirp pulse amplification. We're using direct pulse amplification, And it's mainly related to the fact that for solid-state lasers, you cannot go above something like gigawatt per square centimeter on linear optics, and damage of a dielectric will simply kill you. Here, at 10 to 12 watt per square centimeter, gas slightly barely gets some ionization, if any, but even if something bad happened, for the next shot, your medium is absolutely recovered, and it's absolutely normal. As I said, the beginning of the long journey from a seed pulse to very high power pulses starts from the way we generate a short pulse. We have more than one, but they're all relying on a bandwidth borrowed from a short pulse 1 micron laser. In our case, it is a glass laser, so we combine radiation of a very long 10 micron laser pulse with a very short 1 micron laser pulse. When they mixed up in a Kerr modulator, we have basically a birefringence, some induced short time birefringence, and leakage will be sliced or selected with a short pulse. In 21st century, we can do better because it's a last century technology, very robust, works like a clock for years. We are, along with other groups dealing with long wavelengths infrared, we are, instead of using glass laser, using Tie-Sapphire laser, and then parametrics can ultimately give you a seed of the order of 10 to 20 microjoules. I just placed an order a few days ago for this system because of some DoD support. Well, when we take that short, low energy seed pulse and amplify, as I say, in a high pressure amplifier, what we see, wow, what's going on? We send in a single pulse. We see out train of pulses. Each individual pulse is 3 picosecond long, but number of pulses depends upon the following physics. So if we have 10 atmosphere active medium, shown here with a red color, as you see, there is no complete overlap of lines. I would like to get rid of this. I would love to, but it's too expensive. It may take more than one human life to learn how to run electrical discharges at these high pressures. And as a result, the green pulse, nice smooth bandwidth, here is a 3 picosecond pulse, simultaneously interrogates a couple of vibrational lines, and as you see, some of the frequencies within this pulse will be amplified more or less. We modulate frequency spectrum. When we modulate frequency spectrum, we modulate time spectrum, and the modulation period is a period of distance between individual rotational lines, and everything here looks great because for our measurements, this 18.5 picoseconds is fantastic fiducial. I don't need to calibrate my time measurements. As long as I see a couple of pulses in a train, I know what is the spacing between them with very high accuracy. Then we take this laser pulse to a big beast that we brought. It's a remnant of laser fusion program. It's kind of large machine. And what is the beauty of this large machine? This large machine, I told you, doesn't need to have very high pressure because I'm already on a millijoule level from the previous stage of amplification. Now when I take this pulse and send it in, I'm getting fewer pulses, but more importantly, I'm expanding the beam and extract very large energies. Anyhow, we long ago, Dan Heberberger and I, we built the most powerful laser, 10 micron laser in the world. And where we are right now in 2019, there are two groups that shoulder to shoulder, or rather independently, develop this type of technology. One of them, as I say, UCLA, Neptune. So we have generated multi-terawatt laser pulses. We are currently much more interested to build, and we are building that, a lower power but higher rep rate system, because this big beast is, as you see, for example, this PFN is a 100 kilojoule capacitor bank. So when you fire 100 kilojoules, okay, you cannot fire in a few seconds another one. because that heat, even my conversion efficiency is very, very high, from electrical to optical, still a lot of heat, it has to dissipate somewhere. At the same time, there is ATF-BNL group at Brookhaven National Laboratory. They recently reported at this year CLIO 2 terawatt pulses. And we ran experiments both here, and I will present results. So the question is, why do we push so hard? It took years to build and to go to shorter and shorter pulses. When Ed Moses, who is director of NIF, a scientist who led effort of building the most powerful laser in the world at Lawrence Livermore National Laboratory, he came to our lab, he asked me, so what is your achievement? And I said, over years, we managed to go from 1 nanosecond, or few nanoseconds, which was the pulse length at Los Alamos lab, which was the peak of development, to 3 picoseconds. And he said, what, this is not bad. And that made me feel a little bit better, okay, so I didn't waste. But the bottom line, there are some group of experiments where we can only study with 10 micron interaction with plasmas. One of them is ion acceleration. Well, if I do right now like this, I'm sending a sound wave to all of you. If we are pushing hard sound particles, let's say, classical example, supersonic jet is moving too fast and pushing particles much faster than the sound velocity in air, we are launching a shock wave. The issue is any disturbance that travels at a supersonic speed through the medium ultimately could be launched a shock. Why we're interested in launching shock waves? Because to accelerate ions, and acceleration of ions is a very hard business because it's never done with direct acceleration of ions with laser. We always ask a middleman, which is electron, which is being accelerated by a laser field, and only then ions follow that so-called sheath field or something. We decided to look at completely different mechanism to do that. How does it work? So here, if we are launching a shock wave in a plasma, and that plasma is moving, it's just a layer of plasma with a thickness of around 5 dBi lengths, like a few microns thick, there are two possible scenarios for ions that are located in front of that moving electrostatic potential. First, we can reflect that ion. Second, if ion is too energetic, it will just simply zap through. The condition of reflection of ions and how collisionless electrostatic shock waves work have been established long ago, and conditions very straightforward. The potential of this field must be larger than kinetic energy of ions. And if that is true, then by moving, if possible, that electrostatic shock wave at a constant velocity, ions will gain double velocity of the shock minus some initial velocity. And if that is true, then here is a potential of important and interesting mechanism for ion acceleration. Before we started doing that, collisionless shocks have been considered long ago in the 60s by Sergei. By the way, this potential has his name. It is from his PhD thesis filed in 1966. And very nice theory, simulations following the theory, showing that if you have a certain shock that propagates slightly above sound velocity in a plasma, in plasma that is called ion sound speed, then there is a possibility, theoretical, that it is a laminar shock. There is a mathematical solution to have a soliton-like propagation of shock with a constant velocity that will reflect ions with double shock velocity. And if that pusher or piston or shock is moving with a constant velocity, all reflected ions will gain the same energy. Sounds fantastic. It likes like new mechanism for acceleration of ions. By the way, acceleration of ions, traditional done with RF, is very hard business. Gradients are very small. Everything is bulky, very expensive, and ions is very difficult to accelerate. Well, so what we have done, we took a 10 micron laser piston, focused in a gas jet. Here was a hydrogen gas jet. As you may know, fully ionized hydrogen is a nice source of protons, nothing else here. It's a gas, so no reason to consider what happens with this charge exchange and other ions. Slightly above 5 times 10 to 16, so A naught was 2.5. And it was important for us that because of gas, we could use a green probe and have nice understanding and nice movie by changing time between pump and probe. So what's going on inside? Typically people use foils. We have no idea what happens in that foil because it's opaque for almost anything but X-rays. For X-rays, nobody knows how to build good diagnostics, and it is complicated. So we ended up in a generation of very narrow energy spread proton beams up to 22 MeV over approximately a millimeter long accelerator. As you see, here is how shock wave in numerical simulations looks like. It's a nice, beautiful, as I say, more like a Japanese tsunami picture. Of course, we put colors in real life, they're all the same color because we are talking about the same protons. But again, demonstration of this very narrow energy spread less than 10%, high energy protons was a very nice kind of result. We pursue different ideas here, but again, it will tell you one more time that long wavelengths allowing you to activate completely different mechanism, let's say for ion acceleration, only because for longer wavelengths, gas can be used as a foil, if you wish. Because optically, fully ionized, as I said, atmospheric pressure gas, which is what was here, slightly less than that, is critical plasma density, or that plasma with refractive index for 10 micron light equal to 10 to 0. Well, let me change gear. We're looking right now at nonlinear optics. So now you saw example how high power terawatt and much higher than terawatt CO2 laser could be used for particle acceleration. We also accelerated electrons, but I don't want to put too much of plasma physics on you guys. You are still whatever school of optical sciences, okay? So let's stay with optical sciences. And I will talk about our recent experimental efforts on nonlinear guiding. Well, we all know that if I take this, let's say, laser pointer and shine in a far field, laser diverges. It's a natural phenomenon called diffraction, and we can do nothing about that. However, there is some technology called laser filamentation or nonlinear laser self-guiding that is using not just a linear refractive index of gas or air, but nonlinear one. So when we go to very high fields, very high intensities, we are changing refractive index which is following the initial, let's say, Gaussian distribution. Then this N to I product, perhaps you all took already nonlinear optics class, this N to I product will make a regular slab of air looking like a lens. So now we are focusing, it's called Carousel Focusing, described by this simple formula, and which we are interested in this lambda squared scaling. Of course, if you just activate only focusing mechanism, what will happen? Light will strongly focus and collapse, and the smaller the spot size, the larger the diffraction. But what has been observed long ago in late 90s using 0.8 micron lasers, that actually if you are slightly above so-called critical power for self-focusing, laser beam doesn't collapse. And why it doesn't collapse? Because once you reach certain intensity in a certain space, you ionize, partially ionize air. Usually first starts oxygen and then nitrogen. This plasma works as a negative lens. So if we can find a balance between carousel focusing and plasma defocusing, and people did observe this, then you can guide laser pulse, high power laser pulse, in real atmosphere today until up to kilometer. Canadians and Europeans kilometer. So one would say, yeah, you know, but for 1 kilometer long propagation, we need to have as much power as possible because we have some loss mechanisms anyway in order to do that. And when they do that, they observed something like this. So when you come with a power much higher, like 30 times higher than critical power for self-focusing, the beam, nice beautiful beam, as you see, few centimeter diameter, breaks up in small filaments. Each of them contains energy or power approximately around 1 critical power. And of course, this type of breakup of a beam ruins coherence of the beam. So we are delivering certain energy, but the question is, can we do something better? And for the rest of my talk, I will try to convince you that the answer is yes. And we're trying to use lambda squared, and which means the critical power, or the power at which the beam will see that filamentation phenomenon, is somewhere on the order of terawatt. But I have to say, when we started this in 2015, we didn't know even what is the nonlinear refractive index of air at, say, at 10 micron. People, of course, use some analogies and calculate assuming knowledge of dispersion of air, but I'm an experimentalist, okay? If you have to go somewhere or you do experiment, you first have to at least know what is your critical power for self-focusing. And therefore, we first measured nonlinear refractive index. So what we did, we took two wavelengths, CO2 10 micron pulses, 10.3, 10.6. We propagated them in a several meter long cell filled with air, nitrogen, oxygen, and couple of noble gases. In a classical nonlinear optics, when you propagate light with a medium that has non-zero so-called chi-3 coefficient, we generate sidebands, both Stokes and anti-Stokes components. We then separated one by one these components through this spectrometer and measured amplitude of it. And we generated this type of spectrum of 4-wave mixing of air at 10 micron, as you see. Here's my 10.3 and 10.6, two pump lines. By measuring efficiency of production of these sidebands, we extracted a critical power, first of all, of course, nonlinear refractive index of air at 10 micron. It happened to be not very far away from what people calculated. Our value is right here, 5 times 10 to minus 19 centimeters square per watt. Calculated was close to 4 times again, close, but now we gained confidence. So now we knew that when we go in experiment that we want to observe nonlinear guiding, we need to have at least factor of 2, maybe 2 point something safety factor on a power. So if you take this number and you calculate critical power for self-focusing, you end up with anywhere between 300 and 400 gigawatt. As you see, power is quite substantial. And of course, to be safe, we wanted to have a terawatt laser system.
In argon, you couldn't measure because it was so low, or the error was?
In argon, we went straight to noise. So I believe we measured, but we were not comfortable because signal-to-noise ratio was not good enough. We measured only for krypton and for xenon.
The noise of this is on the order of 20%?
Noise is quite large because windows produce something. Beam propagates in air, produces something. Okay, so this nonlinear optics, especially in gases, is a quite tricky business, I would say. Because here we were limited to remind you, here is rather long pulses used for measurements. So I couldn't go to much higher fields because we observed just avalanche breakdown, and then all these measurements will be thrown out of the window. Well, here is another example of a terawatt system that we used for experiments. The system was built by a group of laser scientists at the acceleration test facility at BNL. As I said, TiSub-5 laser is used with parametric amplifier, used as a seed source. So from the very beginning, ATF BNL used much smaller diameter beams and much smaller aperture discharge modules. As a result, they were interested in decreased intensity on optics of the system. And they build a stretcher, amplify it, and then amplify it, even compressed and amplified more. We have got more than 1 terawatt of power. As I said, currently they are 2 terawatt. But again, the message to take here, our system's rather complicated. In addition to power requirement, unfortunately or fortunately, we still have this pulse splitting. To remind you, it is that because of incomplete overlap of lines, because we're using relatively low pressure, 10 atmosphere, 9.5 atmospheres. However, we did have 3.5 Joule pulses and 3.5 picoseconds in the leading pulse. And pulse here, this is big start, and this is tail. On the tail, we had a couple of post pulses. So we build a setup. So here, if we just take a laser beam, terawatt laser beam, which is exceeding critical power for self-focusing by a factor of, let's say, 2 or 3, theoretically, if I just propagate it in air, nonlinear refraction of air should take the beam and focus it. The problem is, if we just do it naturally using a lens, air, and nonlinearity of air is weak, it will take 200 to 300 meters. As you may know, even national lab doesn't have labs that have that type of real estate, okay? So we put a mirror to speed up the process, produced area when we observed filamentation, have couple of sodium chloride wedges that allowed us to take very little fraction of a beam and analyze spatial, temporal, and spectral parameters of this beam, and had kind of moving these 2 wedges along the propagation path, we could make quantitative measurements and characterization. First, what we observed. It was a LWIR moment, was very simple. You turn off all lights and you see beautiful, nice kind of plasma. And plasma clearly reminded me avalanche ionized plasma, because it's kind of beaded plasma, kind of classical. However, this plasma only lasted approximately 5 to 6 meters, and when we moved our diagnostics, that pair of sodium chloride wedges further down the road, what we observed, that even without any plasma, without any visible plasma, okay? Because what we see only fluorescence. Now what you saw is just CCD camera. It's basically sensitivity of a human eye to some blue light fluorescence of nitrogen and oxygen. And what we saw very clearly, threshold phenomenon. If we exceeded certain threshold experimentally, then instead of a diffraction or slightly affected by Carousel focusing beam, but beam is still diverging, we saw a nice, beautiful channel, centimeter diameter, contained a substantial amount of energy. More than that, this type of channel persisted even at longer distances. Okay? And we summarize all we saw on this figure. And as you can see, the red line here corresponds to evolution of a beam that's supposed to be in a vacuum modeling, giving you absolutely diverging beam, but in real life we observed a centimeter diameter kind of light channel or laser channel. You can see the profile of that beam, and what was really kind of amazing, that inside of that channel we got approximately 1 joule of energy, and that 1 joule of energy was actually, in my opinion, could even persist propagating further and further. Again, just real estate didn't allow us. The rest could be just making a hole in a wall and shining parking lot. In national labs, this type of things are complicated, okay? Possible, but complicated. Okay? Results are very well received, very much interest, published a couple of good papers on that, but we also observed that spectral broadening is very, very modest. Here you can see where is that pump, that black line, and here is measured spectrum. I badly tried to measure high efficiency supercontinuum generation or broadening, spectral broadening of high efficiency. Why? Because the paper published 2 years before our measurements, giving these nice, beautiful results for 30 meters, nice, beautiful broadening, as you see, very high efficiency. So again, one more time, you find out one important thing, that experiment is the queen, as Francis Bacon said, okay? So it's still valid, okay? So until we measure something, you can million times come and discuss what is possible, what is impossible, but again, very good example. I will explain later on why it happens. We also did some measurements of evolution of a pulse. Our initial train of pulses was evolving, and was evolving in the way the following. Once we sent in the train of pulses, we used a strict camera diagnostic to see picosecond evolution. We start losing that post pulses, and eventually in that nice light channel, as I say, where we did not observe any visible or any relatively high density plasma, we observed nice, beautiful single pulse with initial power of 1.2 terawatt in this particular case. We did not resolve time in time domain the pulse using the previous diagnostic. We used so-called diagnostic, I don't know if you're familiar or not, it's a non-collinear second harmonic generation. When two pulses collide in a nonlinear crystal, they cross each other, and now if you do things right, space becomes time. And that type of diagnostic called autocorrelation. We used autocorrelation measurements. Here is how data looks like. So initially 3.5 picosecond pulse, non-guided, got much shorter, and therefore we know that the joule that we measure clearly should correspond to much higher peak power. And answer is very clear, because the head and the tail of this pulse will have powers below critical power for self-focusing, and therefore they will simply will be affected by diffraction. And we summarize our data on this slide. As you see, we kind of in a filament, we produced in air, intensity is clamped or quasi-constant around 1 terawatt per square centimeter. Another amazing fact. Why? Because we know we're guiding laser. We know something is balancing carousel focusing. It means we are producing free carriers. However, there is not a single described in literature ionization mechanism that simply could be applied and explain why 20, 30 times below the tunnel ionization threshold. I don't know if you're familiar, there is a so-called Keldysh parameter where multiphoton ionization is important, and or tunnel ionization. Here is Keldysh parameter is 0.1, where clearly tunnel ionization regime. So again, experiment brought too many questions. Why? How? We know this is data. We know it is very robust and reproducible. And here what happened, we collaborated with a group of Jerry Maloney from Arizona, and for several years before this experiment was staged, they described an interesting mechanism that if you have, in a regular way, single atom ionization that is coming usually for oxygen around 20 terawatt per square centimeter, you see that ionization rate increases, but again, we're down there. So how do we produce free carriers? There is interesting interaction mechanism that Stefan Koch and co-workers, they borrowed from solid-state physics and explain that it is possible that these conditions can bring neighboring molecules and atoms and electrons to produce extra charge that could be actually effectively be working as a seed source. But again, this is a theory. How do we know that it is true? Paris Panagiotopoulos, he ran simulations, and what we observed that when we took into account this new self-consistent microscopic model, we obtained very nice blue circles experiment. Red line is modeling by Arizona group. Very important that many observables, they were consistent with theoretical description. And what is important for us to know that here is, for example, an amount of energy we measured, as I explained to you, that we constantly measured energy preserved in a filament. And here is one simulation show and what experimental triangulars. Here is an explanation of limited spectral broadening. For example, it is generation of odd harmonics, which is a Chi-3 process. And the main reason for that is that dispersion of air at this long wavelength infrared, as you see, we're starting at 10, and then we're at 3 point something, and then 2 point something. And dispersion is very small, so there is a nice phase matched or propagation of omega or pump and harmonics, and that is what to some extent makes phase modulation not so efficient. Well, when we, beauty of a theory or modeling, that in experiment you cannot zoom in on every single individual molecule, but in theory we can. So what happens with nonlinearity, or what happens with propagation of a few picosecond long pulse in air when we take into account this many-body ionization effect? And what happens, here is your curve, which is following the laser pulse. Laser starts from 0, reaches maximum, and again goes down to 0. So if we take into account that ionization phenomenon, which is like again combination of many-body ionization mechanism and avalanche ionization, we see that after certain time we accumulate sufficient amount of free carriers, and it is effectively dumps or balances. So you see, instead of self-focusing, positive numbers here, we see some self-defocusing. And we believe it is, at least currently, it is what happens in the experiment. Let me just summarize. I'm a few minutes from my time. I presented today a status of high-powered and micron lasers that can generate relativistic pulses. To remind you, relativistic pulses, you need at least 1 terawatt in a focused beam. We demonstrated that a new physics, so it's not just wavelength scaling, but new physics phenomena can be studied using this type of high-power long wavelength infrared laser pulses. First, I have shown you some example of what that new physics could be. For example, shock wave acceleration of light ions. One can say, what's the big deal here? Let me tell you something. The United States of America right now doesn't have any single radiation therapy facility more than protons. There is a very strong need and very strong desire to build a state-of-the-art, DoD wants to do it for Veterans Affairs, this ion facility. Medical people say, well, let Johnny in the game. Don't build us a proton facility or more modern. Let's look at what ions will be better for treating radiotherapy, for cancer treatment. And medical people say, we would like to try all light ions, protons, helium, oxygen, nitrogen, up to neon. And I say all these ions can be extracted out of gas. Of course, nobody going to build tomorrow facility based on CO2 laser driven. However, you can take at least some test facility at low energy of power, and instead of relying on Monte Carlo, it's what medical people do, at least measure some radiation efficiency using this type of source. This is something, at least in my mind, maybe for the future. At the same time, we also have shown that for atmospheric propagation, the self-guiding of a joule or terawatt power laser pulses over kilometer distances seems to be possible in a single channel. Channel is large. There is so much here to do you can't imagine, because again, it is changing a game, because instead of millijoules, it is joules, and it is what many applications are interested in, plus it is a new and interesting spectral range. Of course, whatever I told you today is not my own contribution. However, I tried today to cover only research where either it was my solo scening, or maybe with some a couple of collaborators. I would like to say thank you to group at Brookhaven National Laboratory. They helped a lot in our experiments over there. For shock acceleration of ions, I collaborated with a group of Luis or Silver from IST, from Lisbon, from Portugal, and now Frederica, who actually ran codes for me. He is at SLAC, a group theory group leader at Stanford Linear Accelerator National Laboratory. Of course, Arizona group, I would like only to thank all of them, and of course Paris, who did a lot of footwork. And clearly, all I told today is not possible without collaboration of several generations of graduate students from UCLA Neptune Laboratory. At this moment, I would like to thank all of you, and of course, DOE, Air4SR, ONR, and all that organizations that made this happen, because in all these experiments are all rather expensive things, okay? And equipment here, rather expensive things, okay? So this is not, that's something you can do, kind of on a simple, I don't know, one diode laser and one beam splitter and 2 detectors, okay? This is rather expensive, complicated, but it's a lot of fun, and I learned a good lesson. So when, more than 35 years ago, when I came to this field, I chose people. I didn't know much about this, okay? And I chose just people, groups that I liked more than anything. And then kind of life is taking you, and then many times, many of my colleagues told me, Sergei, no, why do you pursue this? No, drop it, okay? There are so many interesting things. There are these TIE-sub-file lasers, God knows what kind of lasers. Over 35 years I'm in science. And what I learned, when you stick to your guns and you do what you like and what you do, then at the end of the day, in 2019, the whole world is crazy about 10 microns. Everyone wants long wavelengths infrared for many different studies. And as I keep telling our students, guys, we're already on Everest, and they are on a ground camp 1 or 0. They need a long, long way to get there, and we are right there. And I hope maybe you will hear something more interesting and exciting about long wavelengths infrared developments. Thank you.